Hello everyone, my name is Dr. Deepak Yadav, and today we will discuss the different basic antenna parameters, how the antenna is actually working with the help of these parameters like radiation pattern of the antenna, transmission characteristics of the antenna, near field, far field, and many other things that we will discuss in the today's lecture. So we will start with a little introduction about what we are going to study today, and this is antenna fundamentals, in which we will study about the introduction and basic antenna parameters like radiation pattern, beam area, beam solid angle. It is represented by ohm A, radiation intensity, beam efficiency, resolution, aperture efficiency, and antenna height. Then we will discuss about the radio transmission link, in which we will study deep in about the fringe transmission formula. Then oscillating dipole, signal to noise ratio, how signal noise power affect the signal power, and how we will deal with the noise power removal, and antenna parameter and impedance matching. So we will start one by one, and this is the basic antenna that how the electromagnetic wave is radiated from the antenna. This is the structure of electromagnetic wave having E field component only, and H field component is just perpendicular to this. So we will consider only there is an E field in the electromagnetic signal. So if the field vector, if we see the motion of the field vector is in this direction, and then that is 180-degree out of shift, and this is the waveguide from which the signal is transmitting from one media to another. And this is actually the part of the antenna that is flaring out of the guided media, so that this electric field vector is trying to match the impedance to the impedance of the free space. So when the impedance is matching due to this flaring out, then the signal is start transmitting into the free space. So this is the source where the signal is generated. This is the transmission line. It may be a twisted wire cable or coaxial cable or metal tube that is known as waveguides. This is the antenna that provides the impedance matching between the guided media to the unguided media, that is free space, and this is the free space where the signal is moved. So when the signal will leave this guided media, that is antenna, it makes the loop like the wave is going like this, and this make the complete loop, and this is the form that is known as the radiation, which is propagating in the free space, as we can see over here. Now this is the basic structure of the antenna that is going to be transmit the wave, in which we have a source that can generate the electromagnetic signals, and this is the load resistance, and this RR is the radiation resistance of the antenna itself. Then what is the radiation resistance? The radiation resistance is a hypothetical resistance that represent the amount of radiation that is that is transmitted into the sphere, the power that is transmitted into the space by the means of electromagnetic signal. The consumption of that power is represented by this radiation resistance of the antenna itself, and this is the loss resistance, and the loss resistance is considered due to the ohmic losses inside the antenna and the waveguide itself. So when the impedance matching is proper, the signal is coming from this way, and it is, if the impedance is properly of the front end of the antenna is properly matched to the free space, the signal is going out from this antenna. But if the signal is, if the impedance is not matches, like antenna is not very efficient, then the signals reflect back to the source and then again to the signal and form a standing wave. So this is known as the standing wave, and we have to avoid this standing wave by properly matching the antenna impedance to the free space. So the signal to reflection coefficient or standing wave ratio is the measure of how much amount of the standing wave is created inside the antenna itself. So the antenna total impedance is now represented by ZL, ZA. Z is equal to radiation resistance plus loss resistance. This is the real part, and J times of the impedance of the antenna itself, that is having the capacitive and inductive component of the antenna itself. Now, when the signal is transmitted into the free space, there has multiple pattern that electromagnetic signal follow when it radiate from the free space. A stationary electric charge does not radiate, and neither does not electric charge moving in a uniform velocity. So, if we see that a stationary charge, that is charge Q plus, is not going to be radiated, or if this charge is moving from a uniform velocity, it cannot radiate any signal. But if this charge is accelerating with a constant acceleration or deaccelerating, it will produce the radiation. It lose or gain the energy in the form of electromagnetic radiation that we can see as a radiation. So, if we see how the radiation emit from a source, then there we have three specific radiation pattern that a radiating element can create. That is isotropic radiation. Isotropic radiation is nothing but a single dot, that is source, that is radiated in the all direction equally. This is in the 2D plane. So, if we visualize in the 3D plane, there is a small dot, and that radiation is going into the sphere uniformly in all the direction. While in case of omnidirectional antenna, the radiation is this is the source, and radiation is making the shape of 8. Like in this and this direction, there is no radiation, while in this and this direction, there is a maximum radiation. So, if we see that in the 3D, if we see that it form a dumbbell shape, shape, or we can say donut type shape of radiation that is transmitting from this unidirectional antenna. While in directional antenna, the antenna is in the one end, and this antenna is provide the signal in a one particular direction, and there is no signal or a very less signal in the another direction, as we can see in the directional antenna pattern. So, this is the basic equation that governs the basic transmission of the radiation signal from an antenna. Here this I dot is the time changing current. So, if there is a current that is changing with the time, that is sinusoidal current, or maybe some another current that is varying, this amplitude is varying with respect to time, then we have to take this parameter in the one form multiplied with the length of the current element itself. So, from the one end of the equation, we have either accelerating current or time varying current and a length of the antenna that is fixed. And the another thing is the in the another end of the equation, there is a charge. There must be a charge having some value plus 1, plus 2, plus 3, or minus 1, minus 2, minus 3. And there is a change in the velocity of the charge itself, not in the position, but in the velocity of that. The charge must not be moving with a uniform velocity or stationary. It must moving with the accelerating velocity or deaccelerating velocity. Then only there is a radiation. So, the basic equation is either we have time varying current or fixed antenna length, or we have a charge and that charge is accelerating or deaccelerating in a particular direction. Then only we have the radiation in the antenna system. So, this is the basic transmission equation for the antenna system. And now, how the antenna is actually working? We have a source that generates the electromagnetic signal. We have a transmitting media. It is either twisted wire cable or coaxial cable or waveguide that carry the signal from the source to the antenna. Antenna is nothing but an impedance matching device that match the impedance of the transmitting media to the free space. By different technique, we can design the antenna so that we can able to match the impedance of the incoming wave to the free space. And then this wave is forming this kind of loop and propagate in a particular direction where the antenna is focused. Now, in the very initial state of the transmission or in very near to the antenna, this wavefront is almost circular, making a circular pattern. But when the distance is going, when the radiation is going away from the antenna and distance is very large, like in kilometers, then this wavefront is almost became constant. So, the sphere is so big, like its surface is almost seem to be a flat plane, as we can see over here. And in that far field, there is a receiving antenna that can absorb only a small portion of this flat wave front that is coming from a distant source, and this signal is received. As the amount is very small, the power received by the receiving antenna is very small. So, the first step is to going through the waveguide, it's going into a receiver, where in the very front end there is a low noise amplifier that can amplify the signal first, and then we have performed different operation like demodulation and amplification. So, there is a different field in the antenna itself that we discussed in the previous slide as well. We have a near field that is known as Fresnel field, and a far field that is known as the Fraunhofer field. In case of near field, the radiation coming from the antenna is having the fluctuation. The wavefront is not properly circular, it is properly flat, it is circular in shape or spherical in shape. So, the radiation is not uniform in all the direction. So, in case of near field, this is known as Fresnel field. There is two, again it is divided into two distant field, that is reactive near field region and radiative near field region. In case of reactive near field region, as we can see, this is the antenna, this is the diameter of the antenna or length of the antenna, and this is R1, that is the radius of the reactive near field, and it is represented by R1 is equal to 0.62 under root d cube divided by lambda, where lambda is the operating wavelength and d is the length of the antenna. So, this is the radius of the reactive field, in which the magnetic field and the radiative field both are exist simultaneously, and there is a large fluctuation in the signal level if we receive the antenna, if we put the receiving antenna in the reactive near field region. While in case of radiative near field region, that is Fresnel region, here the radius R2 is given by 2d square by lambda. So, here the fluctuation, because the magnetic field is bounded up to this limit, there is only a fluctuation due to non-flat surface of the wavefront that is radiated from the antenna. But after this region, the region that is known as far field or Fraunhofer region, where the radiation is uniform in all the direction, and we generally put the antenna in the Fraunhofer region, so that there is no fluctuation due to the size of the antenna and due to the magnetic field radiated by the antenna itself. So, as we can see, the radiation density due to the antenna in the near field and the far field region. In non-radiative reactive region, you can see there is a very large density and the fluctuation is very high, because different waves are having constructive and destructive interference over here. While in this region the density goes a little low, but still there is a irregularity in the transmission radiation. While in case of far field, the wavefront almost became constant and the radiation is very very smooth. So, these are the different radiation pattern parameters. The first is a radiation pattern, another is the directivity, radiation resistance, power, gain, bandwidth, reciprocity, effective aperture, beam density and directivity, then fringe transmission formula. The first is radiation pattern. The radiation pattern is nothing but the radiation that is provided by the antenna, the pattern of the radiation that is provided by the antenna. So, if we put the antenna at the center of this this coordinate system, we have a radiation in that theta is equal to 0 or z direction, and this is known as the main lobe of the transmitting antenna, and these are known as the side lobe of the transmitting antenna, and in the very back this is known as the back lobe of the transmitting antenna. So, the main lobe and the second lobe, there is a gap of 0 radiation, and this gap is known as the null point of the antenna, and the angular separation between these two null point having 3 dB point, that is known as the first null beam width. And if we have a 3 dB point over here and 3 dB point over here and the main lobe, and this is known as the half power beam width, where the power became half and the signal strength became 1 by root 2. So, there is a first null beam width where first null comes, and there is a half power beam width where the power became 1 by 2 of the maximum power, and this is the radiation pattern. So, there is many things, the direction of the main lobe, the direction of the minor lobe, and there is a half power beam width, first null beam width, back lobe radiation level, etc. There is many component that is related to the radiation pattern. So 3 dB bandwidth, I already told you, this is 0 dB power, that is the maximum power that is transmitting in a one particular direction. And this is the side lobe level, which must be below -20. It is like commercially accepted that the radiation level must be below -20 dB level in case of side lobes. So this is the another representation of radiation pattern. This is the rectangular representation of radiation pattern. This is the maximum power. This is the power became half or 3 dB down. This is the dB scale. So this is the half power beam width, and this is the first null where the first 0 is coming, and this bandwidth is the first null beam width in the rectangular radiation pattern. And the field pattern, the power pattern is related by this formula. Power pattern is equal to the square times of field pattern. So almost same, but the power became the square of the electric field radiated by the antenna. Then beam width we already discussed. Normalized power pattern is nothing but the power in a particular or electric field in a particular direction divided by the maximum value of the electric field in a certain direction, and this is known as the normalized power pattern. Its value is always, this is the ratio. So its value is always less than 1 because we divide the complete thing by a maximum value of that parameter itself. So this is the power pattern, this is the electric field, normalized electric field pattern. Similarly, here we divide the power with the maximum value of the power itself. So this is a small numerical where we have to find the half power beam width. So half power beam width is nothing but the beam width where the signal power became half. So it is already given, it is 66 degree. So half power, that is magnitude became 0.707 time is equal to cos square theta. This where the power became half, and we have to find this theta. So with theta is equal to 33 degree, and this theta is symmetrical along this axis, that is 66 is the half power beam width. This is the beam area. The amount of the area that is covered by the main beam is known as the main beam, or a certain radiation that is known as the main beam area. So if you see that if there is an antenna having radiation, then this area is covered by the main beam, and a small area is also covered by the minor beam. So this total area is known as the main beam area in compare with the sphere of the same radius where the radiation is going on. So this is calculated by the spherical coordinate system, where we find the area of this small section and integrate over the complete sphere. So the area of this section, the boundary of this section is r sin theta d phi, and the another boundary is r into d theta. Then we multiply these two things, we have r square sin theta d phi, and when we integrate this small section over the complete sphere and multiplied by the radiation characteristics of the antenna itself, we can find the main beam area of the radiation. So this is the differential area over which we have to calculate the main beam area. So for a circular radiation pattern or spherical radiation pattern, this is equal to integrating from 0 to 2 pi, 0 to 2 pi, 0 to pi, and this is 2 pi over here. When we calculate this value, this became 4 pi r square, which is nothing but the surface area of the sphere itself. Then it is measured in the square degree as well. Then 1 steradian, that is 1 SR, is represented by the solid angle of the sphere divided by 4 pi. So as we know that 1 radian is equal to 180 divided by pi, 1 radian square is equal to square of this 180 divided by pi, or we have this much amount of square degree that is represented a 1 steradian value. So let's suppose we have 4 steradian of the complete sphere. So complete sphere 4 pi multiplied by 33,282, we have 41,253 square degree available in the complete sphere. So to calculate the beam area, beam power, integrate over 0 to pi, 0 to 2 pi, sin theta d theta d phi, we have the beam area value. So this is the normalized beam area equation, and beam area can also be calculated by the half power beam width in the theta and phi direction. And then the power radiation density, it is represented by the pointing vector. Pointing vector is nothing but the electric field and the multiplication of the electric, cross multiplication of the electric and the magnetic field intensity. This is a pointing vector. So the electric field having this kind of electric field vector mount, and this is the magnetic field vector mount, and this making a net that is coming in the direction that is away from this board. So this section is known as the pointing vector that is coming out from this electric field and magnetic field electric field vectors. So if we know the electric field vectors or pointing vector, so over the complete sphere we can calculate the power as well. It is represented by half of real part of E cross H into differential area of that section. So this is how we can calculate the power. Then the radiation intensity. Radiation intensity is nothing but the R square times of radiating density. Radiation intensity is equal to R square times of radiation density. Radiation density is nothing but watt per meter square, and this is watt per steradian. So these are related with the R square value only. This is beam efficiency. Beam efficiency means what is the amount of the power that is in the main beam in compared to the all power radiated in the all beam. So the main beam area divided by complete area of the beam is known as the radiation efficiency, and there is a stray factor, that is minor beam area over the complete beam area. Minor beams are these beams. These beams are the minor beams, minor beam area. Directivity, this is one of the important thing in the case of antenna transmission. Directivity is nothing but the maximum power transmitted over the average value of the power. Like if we have an isotropic antenna that is radiating in all the direction, and maybe it transmit a power P, while if that same amount of power is directed by the directive antenna in a particular direction, the same power, then the ratio of this distance over this distance is known as the directivity of the antenna. It is the ratio, so it is generally represented, it is generally unitless, but it is represented in dBi because the scale is in dB, and with respect to the isotropic radiator, and this I is the isotropic radiator. So scale is in dB, that's why it is represented in dBi, but in actual it is the ratio of the maximum power to the average power over the complete sphere. So this is the formula that is derived, and the directivity is also calculated by 4 pi divided by the beam area of the transmitting beam. So let's take an example, like we have the directivity that is equal to 2. So if we have the beam area of 2 pi steradian and the total beam area of 4 pi, then 4 pi divided by 2 pi, that is directivity is equal to 2. So if we convert this ratio into dB scale, then we have 3.1 dBi representation of the directivity. So if we take a very famous isotropic antenna, its directivity is always 1 because it is transmitting the power of over the complete sphere. So 4 pi divided by 4 pi is equal to 1, and when the directivity is 1, its dB value is also equal to 1. But it's in case of short electric dipole, it is again the famous antenna having a beam area of 2.67 pi. So the directivity is 1.5, or in steradian it is, in dBi it is 1.76 dBi. Then gain of the antenna, it is related to the directivity just by a constant k, where k is always lies between 0 to 1. This is the actual value when we including the losses in the antenna, and directivity is the hypothetical value of the same parameter. So we can also calculate the directivity by half power beam width as well. So this is the directivity, and this is again the calculation if we have 20 dB half power beam width in the theta phi plane. So we have the directivity of 20 dBi. So thank you for this lecture.